gravitational wave from supermassive black holes, and he will speak today about how, I guess, that he will speak about how to detect this with clocks, with pulsars. So go ahead.
Thank you, Nanda, for the nice and flattering introduction. Don't deserve that much, really. And thank you for the invitation. I mean, it's really a pleasure to be to be here again. I mean, I was telling your director that I've been to this campus I think in 2008, 2009 visiting. So it's been a long time, and it's an honor to be the first speaker in person after COVID. So yeah, that's very nice. Right. So in my talk today, I would like to tell you a little bit about pulsar timing arrays, which is a technique that uses pulsars as clock to detect possibly gravitational waves. So I will give you a little bit of an introduction about how we use pulsars as clock to detect gravitational waves. I will talk a little bit about supermassive black hole binaries. Why they come about in the hierarchical clustering scenario of structure formation, and why we expect them to be strong emitters of gravitational wave at the frequency where we can probe them with pulsar timing. And then I will tell you a little bit about the state of the art of those observations and what we have in our data, and give you a little bit of outlook about the future. Okay, so I don't think I have to say much about pulsars. Okay, but for the purpose of this talk, pulsars are clocks. Okay, you have huge masses with a large momentum of inertia. They spin very quickly. It's very hard to change their spin frequency. Okay, so you have, of course, they emit a beam of radio light. They rotate on an axis that is misaligned with the magnetic axis, and then if the pulsar points toward, if the neutron star rotating neutron star points toward you, you have this lighthouse effect. Okay, and so you have a clock that is ticking. Okay, so you have a clock that is ticking. What do you? Well, first of all, you know that there are several classes of pulsars. The one that I'm concerned with are millisecond pulsars. Those are the fastest rotating pulsars, which means also that they are the more stable rotators, right? So they are the best clocks that we can use. And there's about like a couple of hundred of them known in the galaxy. Not all of them are as good as each other. Okay, we have better and worse millisecond pulsars, and we try to use the best, the most stable, as a network to detect gravitational wave, as I will explain in a second. So what is the idea? Well, the idea is that you have a clock, you have a ticking clock, and you try to time to measure the time of arrival of the ticks of this clock, and this is what is called what pulsar timing is about. You build a model for your clock. Okay, you can predict with your model when is going to be the next pulse of your clock. You compare the prediction of your model to the actual time of arrival of the next pulse, and the difference between the two, you call it timing residual. And of course, if you had a perfect model for your clock, and if you had no noise in your observation, this quantity would be 0. Okay. However, of course, observations are noisy. The pulsar profile are not perfect. They change in time, etc., etc. And so this residual is generally different than 0. Okay. Just a visualization of the technique, right? You have your model prediction. Okay. You take the data, and your data don't quite perfectly match with the model, and the residual is the difference between what your model predicts and what the data. The timing model, I mean, this technique has been used for a variety of scientific goals. So, for example, many of these millisecond pulsars are in binaries. Okay, and and the light that they emit to us, so if the binary is almost, let's say, edge on, travels through the gravitational field of the companion, and so you can measure the Shapiro delay, and with the Shapiro delays you can measure the mass of the companion. And this is, for example, how we know that there are pulsars up to 2 solar masses. So all these effects are recognizable in the timing residual. You can include them in your timing model, and you can do a lot of interesting physics with that. So you have to include a lot of physical deterministic effect in order to build a meaningful timing model for your pulsar. But of course, there might be other things in your data. For example, there may be a gravitational wave passing between you and the pulsar, okay? And the idea is very simple. So there is the Earth here, there is the pulsar there, there is an intervening gravitational wave, okay, traveling between you and the pulsar. So a gravitational wave is the perturbation of the space component of the metric. So the space squeezes and squashes in a quadrupolar fashion, like in the figure that you see here. So here you have a wave that travels into the screen. The perturbation is perpendicular to the direction of propagation, and it has this quadrupolar form. So what happens is that since the metric of space is stretched and squashed, the null geodesic along which the photon travel changes in time. And so the time of arrival of the photon on Earth changes as well. So your photon will arrive a little bit earlier or a little bit later, depending on the phase evolution of the wave, okay? And for example, if you have a timing model that doesn't include a gravitational wave and you put a wave in the data, your residual will look something like this, where the red curve is the perturbation due to the wave, and I superimpose some, red, white noise to it. Okay, so this is the key idea, to use pulsars as clock to detect gravitational waves. Now, what about so what type of waves we can detect with this system? Well, the actual delay in the time of arrival, or the redshift, is proportional essentially to the integral. The timing residual is proportional to the integral of the dephasing, let's say, which is essentially proportional to the amplitude of the wave divided by its frequency. Okay, it's an integral of an amplitude. The gravitational wave is an amplitude times a cosine. The integral is the amplitude divided by the frequency of the wave. Now, if you take a massive black hole binary with a chirp mass of like a billion solar mass, you put it at 100 megaparsec, and at a frequency of 50 nanohertz, you get that this residual is of the order of 10 to 100 nanoseconds. And this is very interesting because this is the sort of precision to which we can time the best millisecond pulsars, okay? So by timing millisecond pulsar, a very stable millisecond pulsar, we might be able to detect supermassive black hole binaries at low frequency. Now, the frequency that I put here, the nanohertz frequency range, is determined by your observations. So you time pulsars for many years. So the minimum frequency at which you are sensitive to is the inverse of the observation time. So let's say, a few nanoseconds. And you don't continuously stare at the pulsar, right? You look at the pulsar, you take a time of arrival, then you do something else with the radio telescope, and you do, I don't know, 2 weeks later, you go back to the same pulsar. So the maximum frequency you can probe is essentially dictated by the cadence of your observation. So with this technique, we can see gravitational wave between nanohertz, let's say, and microhertz. And this is where we are sensitive to the slow adiabatic inspirals of supermassive black hole binaries. Okay, so this is pretty much what I just said. So if I take the what I like to call the gravitational wave landscape, you see here so this is frequency versus, let's say, the typical amplitude of your wave. Okay, so you're all familiar with what's happening at high frequency. We detected a lot of compact object coalescences with LIGO and Virgo. At lower frequency in the millihertz, we will soonish, 10-15 years, have the laser interferometer space antenna, which is going to probe what is anticipated to be the richest frequency range for gravitational wave astrophysics. And pulsar timing array sits up here in the upper left corner, and you see the signal that I depicted here is a sort of confusion signal, which is given by the superposition of many inspiraling supermassive black hole binaries. So sensitive frequency range, few nanohertz, typical strain, 10 to the minus 14, 10 to the minus 15. Right. So why okay, we are sensitive to these objects. So why they are interesting? Well, first of all, because we expect at least they exist, right? So for sure, we know that in the center of most massive galaxies, there is a supermassive black hole. And we see the supermassive black holes already at very high redshifts shining as quasars up to redshift 6 or 7, okay? So one of the most interesting topic of modern astrophysics and cosmology is to understand how these massive black holes come about and how they evolve and what is their role in, for example, galaxy formation and galaxy evolution. Right, so we see this massive black holes is just a collection of pictures from the internet. So you see the supermassive black holes. This is the jet of an FR2 galaxy with a supermassive black hole here at the center, a quasar at high redshift. So we see them eating a lot of stuff, right? And we see them ejecting also a lot of matter, okay? So this is what massive black holes do most of the time. And I hope some of you got the reference here. Right, so we have a model for the evolution of these objects. And this model is framed in the hierarchical scenario of structure formation. So we know that galaxies form hierarchically, or at least this is the best, our best understanding of their formation. So if this is just a cartoon of what we call is the merger tree of a galaxy evolution, this is a massive galaxy at redshift 0, and this is the tree of its progenitors. So you see each massive galaxy forms through a sequence of merger of and accretion events of small massive galaxy into ever bigger structures, okay? And we also know that at the center of galaxies, there are massive black holes, and the properties, or I should say the one property that we can faithfully measure of those supermassive black holes, their mass correlates with the property of the galaxy. So this points toward a sort of co-evolution of galaxies on massive black hole. And so one can imagine that, in the proto-galaxies at high redshift, there are massive black hole seeds, and when galaxies merge together, these seeds sink to the center of the merger remnant, and they will form a massive black hole binary. This process is repeated, and in the process, they will accrete matter and shine as quasar and so on and so forth. And so, starting from seeds, merging with other black holes and accreting matter, you will form the supermassive black hole that we see today in galaxies. So, in this scenario, supermassive massive black hole binaries will inevitably form, okay, and will be abundant in the universe. But we don't know much about them, right? We don't know what's the nature of the first seed. We don't know their exact role in galaxy formation, and so on and so forth. Right, so there is a passage here that needs some clarification, which is, when the two galaxies merge, the two black holes form a massive black hole binary. Why is that? Okay. Of course, when the two galaxies merge, so here I show you a plot where is a sort of cartoon, is a chart where you have the relative separation of the two massive black holes. So you go from kiloparsecs up to milliparsec, down to milliparsec. And here is the typical time scale those massive black holes span at that separation, okay? So suppose you have a galaxy, two galaxies merging, right? At the beginning, of course, the two massive black holes won't be in the center of the merger remnant, would lurk somewhere in the outskirts, okay? How did they get to the center? Well, first of all, the first stage is dynamical friction, okay? A massive object in the gravitational field of light particles experience a drag force that slows it down, and of course, by slowing it down, since gravity has negative capacity, you are bound to drift toward the center of your gravitational potential. And this has been demonstrated by a lot of numerical simulations. And I show you one here. So this is my numerical simulation. You have a massive black hole in the outskirts of a galaxy, and whoop, you see, it sinks toward the center. Okay, so those are more serious ones. So those are actual numerical simulation of the process, where you see in some units the relative distance of the two holes, and you see that it sinks quickly toward the center because of this process. However, dynamical friction ceases to be efficient when the two black holes start to see each other at the center, because at that point, they form a binary, and the drag of each particle in your gravitational potential doesn't act individually on each massive black hole, but acts on the binary as a whole. And the effect is just to essentially move a little bit the center of mass of the binary. So dynamical friction becoming efficient, and your binary would stall. And this happens around parsec separation. Gravitational wave emission, however, it's a very strong function of the separation. And if you take a massive black hole binaries and put the two holes at the parsec separation, the time it would take to coalesce because of gravitational wave emission is much longer than the Hubble time. So you need somehow to bridge this gap between parsec separation and milliparsec separation. And there is a number of mechanisms that can help, involving the fact that the binary is not in vacuum, it's surrounded by stars and gas. And stars and gas can act as, as drivers of the evolution of the binary by extracting its energy and angular momentum. So for example, just focusing on stars, although dynamical friction is not efficient anymore as a collective force, individual stars will interact with the binary, will cross the let's say, the binary cross-section, okay? And then you have a three-body interaction, and you have a strong three-body interaction between two massive objects that have a lot of energy and a small star that doesn't have much energy. So because of the system tending to equipartition, statistically, the small star will receive energy from the binary and will be kicked out. That's not a large amount of energy that is taken away, but if you repeat the process millions and millions of times, because you are in the center of a galaxy where you have a huge density of star, this mechanism can be efficient to shrink the binary, okay? So in the years, there has been a picture emerging whereby by interaction with stars or interaction with a circumbinary massive gaseous disk, you might get the two black holes shrinking down to milliparsec separation, where they can merge because of gravitational wave. However, it's a bit more complicated than this, right? So the dynamical friction has to take into account of the clumpy environment of galaxies. So galaxies are not nice and smooth, especially at high redshift. It is not very clear what's the role of gas in the evolution of subparsec binaries. There have been simulations recently that show that actually interaction with the circumbinary disk might even expand the binary rather than shrink it. So it's a difficult, let's say, journey, but we think that we have an handle at least of some of the processes. And in most of the simulation and the calculation that we do, the binaries actually can get to the gravitational wave regime. Okay. So this is the theory, but do we see these massive black hole binaries? The answer is kind of, right? It depends on the scale, of course. Okay. So here it's a scale of relative distance of the two holes from kiloparsec down to merger. So of course, it's easy to see them at large separations because the two galaxies have emerged together. And if the two black holes are accreting, you see them shining as double quasars. And we have plenty of them now. So this is the first example from COMOSA 2003. And those are at, let's say, 2 kiloparsec separation. So they are still early in the merger phase of the galaxy. As you go farther down in separation, of course, it becomes difficult to resolve the two holes, right? And you can actually do a better job if you go at radio frequency. And for example, this double radio core that was originally published by Rodriguez et al. In 2006 has a relative separation of 7 parsecs. So these are two massive black holes, flat radio cores, at 7 parsec separation. The masses here are of the order of 10 to the 8, 10 to the 9 solar masses. So those might be two black holes at the verge of pairing into a bound binary. Okay, we don't know because we don't know exactly the properties of the environment. But this, I would say, is the closest massive black hole binary that is, a secure detection. Everything on these other half of the diagram are candidates, because then at lower separation, when we don't resolve the object, we have to rely on spectroscopic features or, time behavior of the source. And relying on those is very difficult because we don't have really a predictive model for what single accreting supermassive black holes do, right? And therefore, it's hard to build a characteristic signature of a binary when you don't know exactly what the single massive black hole is doing. So one typical, one vanilla consideration is that, okay, well, if you have a binary and a circumbinary disk, the binary has a period. So it's reasonable to expect that accretion will be modulated over the period of the binary. So people look for periodic signatures in light curves of quasars. And this is a famous one published by Graham in 2015, where, but those of course are, you see, those are 2 cycles, right? Really. So what are the chances that red noise produces that? So those are just candidates. I mean, it's very hard to establish them as secure massive black hole binary detections. And here are a couple of more recent examples. So this is a blazar. No, I forgot. You see, I forgot. So you see my email notifications. Here is this is a blazar that is being proposed to be precessing because there is a binary companion to the main black hole that is emitting the jet. And this is a system that came to the that made the headlines a few months ago, which was the famous TikTok binary. Okay, it's another optical light curve, and you see this sort of shrinking periodicity. And so it was suggested that this might be a massive black hole binary on the verge of merging. But of course, if you further analysis of this system revealed that probably this was just red noise. But anyway, so this is the kind of thing that people are trying to get from electromagnetic data. Of course, gravitational waves may come to help, because if you have a firm detection of a gravitational wave from a massive black hole binary, that would be a smoking gun that those objects actually exist, they can pair efficiently, and they eventually coalesce. So this is how a massive black hole binary might look in our pulsar timing residuals. So consider a binary. So first of all, we are not really concerned with the merger phase, because we are seeing the binary early on in the slow adiabatic in spiral. So these binaries are mostly, if they are circular, they are monochromatic. If they're eccentric, they're not, but their orbit does not evolve significantly over your observation time. So here I just play around with some, with some systems, and this is a time 5 years of observation, and this is a typical residual of what could be a circular binary and what could be an eccentric binary. Okay, so this is the kind of residuals that a binary would produce in your pulsar timing array, and you're looking for things like this into your timing data, your residuals that, these are actual data from, I think those are from the Parkes radio telescope in Australia. Actually, it's much more complicated than that, because, those are slowly adiabatic and spiraling binaries, right? So there isn't one source. It's not like looking at binaries with LIGO and Virgo, where you have mostly noise, and then every now and then, whoop, you have a signal, right? So here, the universe is filled with this binary. So by taking a picture of the sky, you will have sources emitting pretty much everywhere in the sky at different frequencies at different redshifts. So what you're going to see is a collection of signals coming from all those binaries. Okay, and you can work out the theory of it, and the typical strain that you see as a function of frequency, essentially as a spectrum that goes with the frequency to the -2/3. Okay, if you take a typical population of binaries that are evolving because of gravitational wave emission, the superposition of their signal will produce a stochastic foreground with a typical power spectrum that goes with the frequency to the -2/3. Okay, and this foreground is produced by thousands and thousands of supermassive black hole binaries. So if you take those binaries and you build up the signal, this is an example that I built from a mock population. Here, well, there is some cutoff because I didn't want to plot everything, but here each triangle, so this is frequency and this is typical strain. Each triangle is the emission of a binary, and the overall signal is the upper envelope here. So you see, at low frequency, it's like a superposition of signal. It's really what we see is a red noise. And at high frequency, where binaries become sparser and sparser, actually you might have individual sources that pop up, okay, and you might resolve individually. So this is the type of signal we are seeking. And if I take this and I inverse Fourier transform it and put it in the timing data, it would look like the red curve. So this is a typical red noise because it's red. If it was blue. Anyway. Okay, and this is an example in two different pulsars. Okay, of course, it's not enough to detect some red noise in a pulsar, because pulsars do crazy stuff most of the time. I mean, they are very stable clock, but still they have all sorts of noises, right? So here is an example. Okay, so the idea then is to correlate signals from a family of pulsars. So to build what it is, a pulsar timing array. And the idea is that you time different pulsars at different spatial locations, and if there is this foreground of gravitational waves, this will show up in the residual of the pulsars in a specific way, okay? And the residuals will correlate in a specific manner that I'm going to show you now. This is the correlation function. So this is how correlated are expected to be the residual as a function of the relative separation of two pulsars, okay, if there is a gravitational wave background, okay? So you see, if there wasn't any, this mean correlation you would expect a zero correlation, because, you know, what a pulsar is doing is pretty much independent of what another pulsar is doing. So this correlation has a specific quadrupolar shape that was worked out by Hellings and Downs in 1983, and is called the Hellings and Downs curve. So the precise shape of it, you know, needs to be worked out with relatively contrived calculations, but you can get a sense, you can get a grasp about why this happens. So the thing is that, suppose here is the Earth, and here are two pulsars, right? If there is a gravitational wave passing by, if I'm looking at the two pulsars at the same direction, when space is stretching in the direction of a pulsar, it's stretching also in the direction of the other pulsar. So you expect the delays, the time residual, to be positively correlated. On the other hand, if the two pulsars are at a right angle with each other, when space is squashing for one pulsar, it's squeezing for the other, right? So you expect the residuals to be negatively correlated. And of course, if you go antipodal, again, you expect the residuals to be correlated, okay? So the quadrupolar, the form of this correlation curve comes from the quadrupolar nature of the gravitational wave. Okay, so let me, okay, I am not gonna go very technical. This is just to say that, you know, we have a full Bayesian framework to detect this stuff. And in the likelihood function, of course, in the correlation matrix between the pulsar, there is the functional form of this Hellings and Downs curve. Okay, so we are looking for this correlation into our data. All right, so what do we use? Well, we use big radio telescopes. There are three main collaborations worldwide. The European Pulsar Timing Array that makes use of the 5 big radio telescopes in Europe. Nanograv, which, well, I should maybe put another figure here, which was using the Arecibo radio telescope, now is mostly using the Green Banks radio telescope. We have Parkes in Australia, and then more recently, actually, we have new additions to this collaboration. We have the Indian Pulsar Timing Array that is now joining the party. The Chinese Pulsar Timing Array using FAST is still in the building and then in the making. And then we have Meerkat in South Africa that is, you know, producing beautiful observations and very precise observation of millisecond pulsars. All these folks here join forces in the in the International Pulsar Timing Array, and so we share data. You know, it's a weird environment. I shouldn't. This goes on YouTube, right? I shouldn't say it. It's an interesting environment, right? Because we are competing and collaborating at the same time, and you know, so it's a. But so we try at least to share data, to build common data set, because of course, by stacking together our data set, we get more sensitive to this type of signals. So this is just to give you an idea of where the location of the, I think those were 49 pulsars that were in the first International Pulsar Timing Array data set. Okay, so let's see, what did we expect? So here I show in this colorful plot, I show a progression of, let's say, theoretical predictions, okay, and upper limits. So you remember the typical signal is, you know, a power spectrum that goes with f to the -2/3. You can describe it as a function of its amplitude, and those are upper limits on this amplitude, okay? That go down until 2018. And here, essentially, what I did was to build by fun. I mean, for fun, I just gave equal credit to each model, and I construct the cumulative PDF of the models. Not very scientific, but, you know, just to give you an idea that we are starting to dig in the range where we expect this signal to be. So those are upper limits, and this is like an upper limit, how an upper limits look like. Okay, so those are the 6 best pulsars of the European Pulsar Timing Array back in 2015. Of course, you have 6 pulsars, you have 15 correlation points. We are trying to detect these, you know, Hellings and Downs correlation, and you see that our data are perfectly consistent with it. And they're also perfectly consistent with 0. Okay, so this is just you know, you can use those data to put an upper limit on the amplitude of the signal. And then, we did some studies saying, okay, if we don't detect a signal to this level, what we can rule out in terms of massive black hole binary population, like, what region of these models we can scrap. Okay, this still all, is the first kind of things that you can do with this type of data. Now, why this come up with it? This should be, I don't know what happened here. This should be much bigger. So remember the data, so the signal is not actually smooth, right? It's not just a perfect power law, right? But there can be spikes popping up because you might have a massive black hole binary that is particularly massive or particularly nearby, right? And this might show up as an individual source. So this is just to say that we also have a Bayesian way to search for those, and we can produce, we can try to detect these individual sources, and of course, so far we just produced upper limits, and this is the this is the upper limit of an amplitude of individual sources as a function of frequency that we get from, again, this was the 2015 EPTA dataset. And if you have a limit on the amplitude as a function of frequency, you can say, okay, if I have this limit on the amplitude, I know that in that frequency range, up to some distance, there cannot be a massive black hole binary above a given mass. So for example, we can rule out the existence of a massive black hole binary of more than 3 times 10 to the 9 solar masses to the distances of the coma cluster, for example. What does it tell you? Well, really not much, because if you take a typical massive black hole binary evolution scenario model, you don't really expect to be any supermassive black hole binary of that mass closer than the coma cluster to us. Okay, so still, those are very weak constraints that we are placing with those observations. So let me skip this. However, things changed in the last couple of years. So you could already see here that those upper limits, so this goes down like a Moore's law pretty much, but then they started to saturate around 2015, 2016, up to the point when, 2020, Nanograph collaboration published their a paper where they claim they find a common red signal in their data. Okay, and this is the red point here. Okay, so let me skip some of the details here. This is what they infer from their data. So this is the common power spectrum of the residual. You see, you have like this white noise at high frequency, and then at low frequency, you see there is this. There are these 2 points rising up, and those are clear detection of a red signal that is common to all the pulsars. And if you take a stochastic gravitational wave background with an amplitude and a slope, right, you can actually try to put the measurements of the power law, slope, and amplitude that you get on a plot, and this is what they get. So this is the slope of the power law. This is the amplitude. Actually, there is a technical thing here. The slope here is 3 minus 2 gamma, where gamma is this. Okay, so minus 2/3 here is minus 4.33 here. It's 4.33 here. Okay, so this is where you would expect a stochastic gravitational wave background to be. Okay. And you see what they are, the region they're constrained is kind of consistent to, the expected, let's say, slope, okay? And they infer a common signal, and if it was a gravitational wave background, this amplitude would be of the order of 2 times 10 to the minus 15, which is relatively high, but is consistent with some of the theoretical models that we have. Now, remember, a common red signal doesn't tell you anything. You want to detect the correlation. And there isn't really any significant detection of the quadrupolar correlation yet, okay? So this is an interesting common red signal. But of course, until we have a strong evidence of the correlation, right, any strong claim cannot be made, okay? But also, I mean, you expect this, right? Because when you have these, let's say, off-diagonal cross term in the correlation, that actually is much, much smaller than 1. So if you have a stochastic gravitational wave background, the first hint that you would expect to see in your data is a common signal, and you would expect the correlation to show up later on because they are much, much smaller. Okay, so it's not, let's say, it is not unexpected that you don't see any correlation to start with in this data. Okay, now this is some work that we did following that that detection, just to point out that the region that they probe with, they measure with nanograv is perfectly consistent with mock populations of massive black hole binaries. Okay, so remember, I told you that this should be like a power law with this, slope. But of course, since signals are sparse, right, you might have bright sources to pop up in your data, and if you try to fit a spectrum, right, it's not going to look like an f⁻⁻⁻³ power law. So here we made like a massive realization of like hundreds of thousands of universes, and we measure the amplitude and the gamma that you would measure with the nanograph signal, the nanograph data, and this is the region that you would measure. So you see what they get is broadly consistent with expectation from massive black hole binary population. And we felt like putting out this paper because, following this detection, there were like, I don't know, 200 papers claiming that, this is clearly inconsistent with massive black hole binaries. So there has to be like dark photon fluctuation from the early universe, whatever. So pick your cosmological model of your choice. Which might well be, but it is perfectly consistent with the type of signal that we expect. So by virtue of Occam razor, I would prefer to, this interpretation rather than some exotic model. Right. As I said, this is rather the amplitude of this signal is rather high. And it's interesting because it already allows, so by taking for granted this is a massive black hole binary stochastic background, which we cannot, but just supposing that it is, since it is on the high end of the expected range, it allows you to put interesting constraints on the massive black hole binary population. And this is what we did in this paper. So essentially, so this is, let's say, in amplitude and frequencies, this is the prior range from, a series of synthetic population models that we expected. And this is what would be constrained by the nanograph data. And if you put that constraint together, what you find is that you can constrain some of the properties of the massive black hole binary population. So for example, you can constrain a lot the mass function of these massive black hole binaries, and you can measure a couple of interesting parameters. Now, without going into details here, this τ0 here is the typical time to coalescence that two binaries take, the two black holes takes from since when they form, up to their merger. So you see this typical time scale here is less than a giga-year. So this detection would tell you that massive black hole binaries following galaxy merger merge efficiently, okay? And this other plot here on the bottom right is essentially the normalization of the M black hole and bulge correlation. Okay, so this, there's a number of values in the literature that span a significantly large range. But since the signal that we see is so high, of course, it would favor a very high normalization for this relation. So you see already, if this is a detection and if this is the amplitude, right, you could already put interesting astrophysical constraints on the massive black hole binary population. Okay, so how am I doing with time? Well, not too bad. Still have, you didn't give me the 10 minutes yet. Are you sure?
No, because I wasn't.
Okay.
So 10 minutes.
10 minutes. Okay, hopefully you were not the only one. All right, so this is just to say that this hint of a common red signal has been confirmed by essentially all the data sets that we have. So from the nanograph data set, the Australian, the Parkes pulsar timing array data set, the European pulsar timing array data set, and of course also the international pulsar timing array data set. So this is an example from, this is the European pulsar timing array. So again, you have this rising common red signal. And this common amplitude is of the order of between 1.5 and 3 × 10⁻⁵. pretty high, but it's there, and we need to understand what it is. Now, just I don't have really slides about this, but just to tell you a little bit more. So we now collected a lot of more data, and we are all analyzing those data. And the signal, it's fairly interesting because there is clearly a common signal in our data, and it has like funny properties. So, it's not Ellingson down. There's not, it's more like a monopole. I mean, there is funny things that we don't understand. So we need to figure out, and really this is the state of the art, right? We need to figure out what is the correlation of the signal, and whether this correlation is due to something physical or something we don't understand in our data, or some funky way we are processing our data that produces this type of correlation. So far, really, I mean, the state of the art, it's really that we don't know whether this is real or not, okay? And we are really, all the collaborations are investigating the nature of the signal that you're seeing. So of course, we all hope that it's gonna be a signal from a massive black hole binary population, but really, I'm not hiding anything. It has weird properties, and we don't understand really what this low frequency signal is, okay? And now if any of my collaborators watch this on YouTube, what are you saying? Don't disclose information. Okay, so just to wrap up, of course, pulsar timing, it's nice to detect the stochastic gravitational wave background, and you can get interesting information from this, from it. But of course, it would be even nicer if you could get like individual sources, right? Because then, of course, if you get an individual signal, thanks to the fact that you have many pulsars in the sky, you can triangulate the signal from the many pulsars, and you can actually get the sky localization of your massive black hole binary. Now, with pulsar timing, you don't get the sky localization with great accuracy. We're talking really about, tens of square degrees. But, which of course, if you talk to an astronomer, oh yes, it's there within tens of square degrees. You say, thanks. But the cool thing here is that, moreover, since those signals are essentially monochromatic, you cannot even break the mass distance degeneracy. So you don't know at what distance it is. So really you have like 50 degrees in the sky, and everything is there, is game, right? You just look for a signal. But if you have seen it as an individual source in PTA, it has to be really bright. So it has to be either really massive or really close, or both. And in fact, you can draw lines in the mass redshift diagram, corresponding to fixed value of amplitude. Okay, so if you see a single source, you can say, really, this is the amplitude, really there are only 40 or 50 galaxies in your 50 square degrees that can host a binary. And then, of course, you can go and take all the data you have for those galaxies and see for potential signatures. For example, if those massive black holes had even a small amount of accretion, right? Since they are so massive and so nearby, you might see them in your electromagnetic data, and there is a whole bunch of signatures that you expect from these massive black hole binaries, right? So you might have periodicities, of course, and of course, if you see the gravitational wave signal, you know exactly the period of the binary. You can match the periodicity of whatever electromagnetic signal you might have. You can expect, variability of the broad emission lines. You can expect variability of the K alpha, the K alpha iron lines, for example. So there is a whole plethora of things that you can go and check for if you have a gravitational wave detection backing up the fact that somewhere there is a binary with this frequency and this mass, more or less. Okay. All right. So this is pretty much the status of things. Of course, the future looks really bright for this endeavor because Meerkat started to take data in 2017. They produced their first data set. They published their first data set last April, and it's beautiful. I mean, the error in the timing residual, which is like 5 to 10 times better than what we get with any other PTA. Unfortunately, of course, well, they have been taking data for 2-3 years, right? So the data set is very short. And since you are mostly trying to detect a red signal, you need to build up your data set in order to be able to, detect what you're after. But really, I mean, this instrument is amazing. And of course, there is FAST in China that is discovering a lot of new millisecond pulsars in the Northern Hemisphere. And eventually, Meerkat will dive into the SKA that really will produce a leap of a factor of 10 in our sensitivity to PTA. So in fact, we are sort of here right now, and really with SKA, we'll really go down like more than an order of magnitude and probe the whole signal, see individual sources if they're there, and of course, do amazing science with it, right? You can think of it about about us doing physics with the CMB, right? Going from seeing a first hint of a, of this background of light, right, in the 1964, right, to make a map with WMAP and Planck, where you can extract a lot of physics, right? So this is pretty much the same. At the beginning, we are going to see something and say, okay, maybe there is a population of massive black hole binaries. But in 20 years, with 20 years of observation of Meerkat and SKA, we could really resolve sources and make this map, much more informative and learn a lot more about, massive black hole binary astrophysics, assuming that those signals are from massive black hole binaries, right? Because of course you might have also some other interesting surprises at this frequency. Okay, so this is my summary. I leave it there. So, and well, stay tuned for more news, because I think within the next year there will be many more results published on this. And thank you for your attention, and I'll take any questions.
Very interesting. Questions? Yes. Diego.
Thank you very much for the talk. Very, very nice. I want to understand whether the following statement that I'm going to make is correct or not.
Okay.
Is it true that with pulsar timing arrays, observing gravitational waves in this way, you cannot actually learn much from the individual system that produce the gravitational wave, differently from the other types of detecting gravitational waves, in the sense that with PTA, it seems to me that you only get access to knowledge regarding the population of gravitational wave emitters, but not the individual. This is true or not?
Okay, so the question, I should repeat the question. I should repeat the question for you too. So the question is whether it's true that with pulsar timing arrays, you mostly gain knowledge about the collective population of gravitational resources rather than individual systems. So the answer is it depends. And it really depends because this population is largely stochastic, right? You have a massive black hole mass function, but the actual realization of the universe of that it actually happens in the universe of that mass function might be something like this, that has a lot of nearby massive supermassive black holes, or can be something where by chance you don't have this very bright system and everything is down here. So it might be that just because of stochasticity, and here we are talking about small number statistics, right? We might observe for many years and just get the background, and of course, we can measure the shape of the background and so on and so forth. And in that case, if we are, let's say, unlucky, okay, we really get mostly information about the overall population. But it might also be that we are in a situation like this one. And in a situation like this, we might be able to resolve individually. First, as like, you make your map and you get like hotspots. And then by observing more and more, these hotspots start to become clearer and clearer, and you start to identify those as individual massive black hole binaries. So in that case, you will have access to individual sources. It is still true that it's going to be much harder to measure their properties. So you can measure the frequency, of course, but since the signal is very low frequency and the evolution, the binaries do not evolve much, well, they are essentially monochromatic, right? You cannot get, for example, the masses or the spins of the holes as you do, for example, with LIGO-Virgo observations. So that's true. So the knowledge that you can get from individual systems from the PTA observation alone is certainly not at the level of the knowledge that you can get with the ground-based interferometer or you will get with LISA.
Thank you for that. I have probably very specific question about the correlation you showed this curve, right? So why is 0.5? Much imperfect correlation 0, 1, and why at 180 is something like 0.2.
Okay.
0.5.
So the question is essentially where exactly the shape of this correlation come from. So why at 0 doesn't go to 1 and why it's different than 0 and 180 degrees. So the reason why it's different is because you have to take into account for the geometry of the system, and the geometry of the system is different whether the source comes in the same direction as the pulsar that you're observing or it's opposite. So this is like, I mean, mathematically you have to write down the antenna beam patterns, okay? And the antenna beam patterns are not symmetric. And it turns out that essentially you have this factor of 2 difference. The reason why it's not 1 there is because, so I really skipped on this. So if you notice when I show you these residuals, you see that there are more curves, right? So essentially with pulsar timing, if I go back, sorry, this is too much. We are in the short wavelength regime. So really the wavelength that we are probing is much shorter, of course, than the distance between the pulsar and the Earth. So that if you integrate along the null geodesics, essentially what you're seeing is the gravitational wave shaking the pulsar. So the perturbation, the metric perturbation at the pulsar and the metric perturbation at the Earth. So now what is the thing? The thing is that if you're observing 2 different pulsars, the metric perturbation at the Earth is the same and is correlated. But the metric perturbation at the pulsar is uncorrelated. So when you do the correlation of the 2 residuals, the maximum correlation that you get is 0.5 and it's not 1. So that's the reason why it doesn't go to 1. There was another there.
Yeah, I would also want to thank you for this talk and thank you for disclosing information. I'm
just saying that we don't know what we see.
A few slides after this one, you have this plot where you're showing the major rates and different scenarios how you can put together the black holes. Now, it was. Wait. No, it was.
Stop me.
No. You have this curve where you merge and you have other possible scenarios.
Okay.
So I was wondering, because I see this analysis, it's extremely interesting how much it can do with individual sources or the background. But it seems that it depends on what is the actual time scale and what is the actual mechanism from bringing the merges. And I was wondering about, from cosmological simulations, we know that you might merge multiple galaxies. If the massive black holes stay around for too much, you're going to have a 3rd one and the 4th one. Then you have little quasi mechanism. And maybe you have, for a long period, small amplitude signal, and very quickly individual objects merging. So this is kind of a pessimistic scenario, because you might miss before. So how much does it depend on this process? So how far away are we from exploring this scenario? Okay,
so the question is about, well, essentially the importance of multiple, let's say, massive black hole interactions, right? If the massive black hole binaries stay around for a long time, like giga years, of course, in the hierarchical clustering scenario, there might be a subsequent merger that brings a 3rd massive black hole. And so first of all, thanks for the question, and I'm here today and tomorrow. If you're interested, we can talk a lot about this. So this scenario has been explored extensively extensive. It's been explored in few papers, and in fact, we worked out scenarios where essentially we just assumed that the binary stalls when it forms. So you can take a semi-analytic model. In the semi-analytic model, you take when two galaxies merge, you form a binary. You take after a dynamical friction timescale a binary form, and then you say, okay, forget about hardening. I just leave it there, and the only thing that can make it merge is the arrival of a third massive black hole binary. So we carried out a number of three-body relativistic integration of these things, and so that we could attach to each triple system a probability of the outcome, whether you merge one of the binary, whether you eject the thing, and so on and so forth. So what we learn from there is that even in this pessimistic scenario, the income of a third massive black hole binary following a subsequent merger would let at least 25–30% of the pre-existing massive black hole binaries to merge. Okay, so even if you have a Stalin scenario, you don't suppress completely the signal. Okay, those binary, the merging binary, most of them are going to be more eccentric because, of course, you can have Kozai-Lido resonances, or they can merge because of chaotic interaction, and at some point, two black holes come very close to each other, and they are capturing very eccentric orbits, and then they quickly merge. You might get the signature of that events in the signal, in the sense that your spectrum, instead of being a power law f to the -2/3, might have a sharp turnover at low frequency, because if you have a lot of eccentric binary, you are emitting most of your gravitational wave power at high frequency. And this is something that has to do with how gravitational wave emission works. If you have a very eccentric binary, instead of emitting at twice the orbital frequency of the binary, you are emitting mostly at higher harmonics, because that correspond to the frequency at the periastron passage, essentially. So this has been investigated, and well, not as much as we would like to. I mean, we don't know exactly whether you might, for example, detect an individual burst from the periastron passage of a binary, and so on and so forth, because we're not thousands of people working on this topic. But it's certainly an interesting possibility. And if you want to chat more about this, either later or tomorrow, I'm around.
Other questions?
Do you have students? Questions from students? Those are all students. Those are all students.
Yes.
You have another one, okay. But you're not a student.
For timing.
No, it's not.
For timing in general. So you need to correct for the actual motion of your radio telescope, right? So how is the seasonal variation of the Earth's rotation taken into account?
Oh yes, that's a good question. So the question was, about the fact that you have to take into account that the location of your telescope when you time your pulsar. And in fact, what we do, we refer all the time. So we measure the time of arrival at the telescope with the local atomic clock, and then we translate the time of arrival at the solar system barycenter. So this procedure requires you to know where the solar system barycenter is. And if you consider that you have a timing precision of tens of nanoseconds, and you translate it into distance, you need to know the precision of a solar system barycenter to what? Now I can't do the conversion, but like hundreds of meters or something like that. And it turns out that we do not know the position of the solar system barycenter that well. And in fact, at some point a few years ago, we started to see the motion of the planets in the timing data, because of course we were referring it to the solar system barycenter, and then you see this sinusoid in your data, like, oh, what's that? And then that sinusoid has a period of 11.9 years, and it's like, wait, this is Jupiter. because the solar system ephemeris are usually, I mean, we use some solar system published solar system ephemeris, which are usually measured to a certain degree of precision, and they are constructed for specific purposes, right? They're not constructed for pulsar timing arrays, right? So, for example, the position of Jupiter or the mass of Jupiter is not estimated good enough for our purposes, because everything counts when you try to determine the solar system barycenter. So, in fact, what we do now in our data analysis, we include a common, I mean, you can fix the solar system ephemeris to the value that you trust best, or you can include them as a common signal that is correlated as a dipole. Because of course, if you mess up, since everything is in a plane, right? If you mess up the solar system ephemeris, the center of mass is gonna do something like this, and so you're gonna see that as a dipolar correlation. So we can fit for it, and we include this in the analysis as well.
But my question was also to the Earth's rotation, right? So this is,
oh yeah,
this moves,
oh yeah, this is all taken into. I mean, this is all taken into account in the mathematical function that converts the time of arrival at the telescope to the time of arrival at the solar system barycenter. I think everything is done at least every effect is first, second, third order, until it's as long as it's smaller than a nanosecond, we really don't care. So everything that is bigger than a nanosecond correction, it's taken into account, at least for the things that we know. So that okay, so that okay, if you're referring to the motion of the Earth around the Sun and the nutation period of half a year, so we know that we don't have much sensitivity at those frequencies. And in fact, if you look at this plot, oops, wrong way. If you look at what are the single source limits, right? This is the rotation period of the Earth. And you don't have sensitivity at 1/1 year, because of course you can always refit essentially the deposition of the pulsar. And you have and there is also an harmonic somewhere here. This one is the second harmonic. No, okay. This is the rotation of the Earth around the Sun. The rotation of the Earth, we don't really care too much here, because it's at much higher frequencies, and we are not as sensitive at those frequencies, first of all, and second, the sensitivity does this, and the astrophysical signals that you expect do this. So at high frequency, you really don't expect anything.
It's nowhere, but okay. I will ask you later.
Okay, we can chat there. Fine.
Other questions? Yes.
When you mention the individual sources and you say that they are nearby, what do you mean by nearby?
So what do I mean by nearby sources? In general, now I don't have a plot here, but when we construct mock signals, mock universes, and we extract the individual sources that we can see, in general, they are most of them, they cluster at redshift between 0.1 and 0.3. So they are like, couple of hundred of megaparsec up to a gigaparsec at most. If they are farther, they start to be swamped into the stochastic background. So yeah, so I would say gigaparsec as a reference distance. So they are nearby, but not as nearby. I mean, of course, if there was one at 10 megaparsec, of course we would see it very loudly, but the chances, of course, are very small. But yeah, so those are the typical. So it's completely the individual sources that you can probe with pulsar timing are completely orthogonal to what you can see with LISA and space interferometers. So they give you like two different pieces of the puzzle, if you want.
Sorry, no.
I have a question. It's a basic question, but so from the correlation that we have seen, how can we determine the localization of the source?
Okay, so the localization of the source. Of the okay, now I'm going to say a lot of not exact things. So this correlation is what you are after if you want to see the stochastic signal. So if you're looking for the incoherent superposition. If you want to check if there is an individual source in your data, what you do is a match filter. You do a match filter technique. So what you include in your data, and it's here. So what you include in your data is a deterministic model for the source. So this deterministic model depends on 7 parameters, and 2 of those parameters are the theta and phi angle in the sky, right? So you explore the parameter space and look whether you find a signal like this in your data. And if you find a signal, you can estimate the parameters, do an MCMC, a multi-nested sample, whatever you want. You can estimate the parameters, and that gives you the sky location in the sky. The reason why you can measure the sky location is that if you have different pulsars in the sky, depending on where the source is, the signal amplitude is going to show up differently in the different pulsars. So essentially, you do triangulation. Essentially, that's how you get the information on the sky. And you can in fact show. You can in fact show analytically that you need at least 3 pulsars to be able to infer where the signal comes from, which is what you do with the GPS and inform, essentially.
But do you need to determine the localization first to detect the correlation, or?
No, you don't need. So here you can do a blind search. So you can just say, okay, I have a signal I expect a signal like this in the data. And I just search if I see anything like that. Of course, if I have a hint, suppose that someone tells me, oh, look, there is this amazing electromagnetic signal at this frequency in that galaxy there. So I can fix the frequency and the location in the sky of the source that I expect to detect. And I can do a targeted search at that location, at that frequency. That would shrink the parameter space of my search and would make my data set more sensitive, right? So you can use information that you have previously collected to, dig deeper in the data, but it's not necessary in principle. You can just do a blind search by, saying, okay, this is the model, the deterministic model of my signal. Let me search in the data whether there is anything like this. And this is essentially what it is done in LIGO Virgo. You have a deterministic model for the waveform, and you just search your data, you measure data until you find a spike in the SNR and say, oh, wow, I have a binary with these parameters here.
But then in principle, to connect also with Diego's question, so let's say that a signal of this kind is detected in your future residual in America, or SIA, then you know more or less the region, but then you can use other bands, the period. So you go in LSD or you go whatever field in there, you fold all of the sources there and you pick up the source.
Exactly, yeah. So
there is a way to pick up the source if it's a single one.
Oh yeah, sure. I mean, you can do it works either ways, right? You can have like an information from a candidate and check in your PTA data if you see something there.
Yeah.
Or if you have a good handle on the fact that there is a sinusoidal wave coming from there, you can just get all the data for the massive galaxies that you have, take new observations, and try to see if you can match the signal. So the period, yeah. So it's this is probably this is likely something that is going to happen maybe 10 years from now when you get like more Meerkat and SK data, but it's certainly an interesting prospect in the future, and it's on the same time scale of LISA, right? So it's not really that far in the future after all.
Okay. Any further fast question from students? No. Okay. If not, let's thank Alberto.
Thank you.
Thanks a lot. If any of the students want to come with us for lunch today, come on. We have 2 more places.
Two more.
It's for free.